Okay, so the last type of problem we're going to do is another form of a horizontal circle, but in this case, you're going to have a person that is going to be spinning around in a centrifuge type scenario. This is an amusement park ride that some of you may be familiar with. It's called the Gravitron. There are other names for it, like the Crazy Silo, in which the floor drops out of the bottom of the ride. It is an interesting ride in that you're in this spinning device, and your back is up against the wall, and it feels like you're pinned against the wall. You can float, and that is going to be because friction is going to hold you against the wall, and your own inertia is trying to get you to leave the circle. So if we take a look at your back against the wall, we'd have a wall. We'd have a person with their back against the wall. Their legs are hanging down here or something like this. Legs have to be attached to their body. And there would be personal inertia pushing them outward. And there would be a force of the wall itself pushing back in. This is acting like the normal force. If we were to turn this thing 90 degrees, you could see this would be the force that would be pushing straight out of the ground. That normal force is going to be countering the gravitational force by amplifying the friction. The greater that normal force is, the greater the frictional force is. And that normal force is going to be connected to the force. The normal force is actually the centripetal force in this case because it's the only force acting towards the center of the circle. And so that means that the normal force is equal to mv squared over r. So when we set up our friction equation, which is usually the normal force times mu, this now becomes the frictional force is equal to mv squared over r times. And we said that we want to be held in balance here, so the sum of the forces needs would equal the weight down plus the frictional force up. Or in other words, the mg has to equal mv squared over r mu. So immediately you hear mass cancels out. Isn't this great when mass cancels out? It doesn't matter how much your mass is, as long as it's spinning at a rate, you're able to stay in the curve. And so this then simplifies itself down to being v is equal to gr divided by mu, take the square root. And that is the velocity to keep you in the curve. If you know your coefficient of friction, you can solve this problem and with the radius for the velocity to keep you pinned against the wall. Anything higher than this velocity, you will be fine. Now, this also allows us to go back to that bank curve equation, because in reality, what this is a bank curve at 90 degrees. And so when we look at the bank curve equation, the minimum bank curve equation, v is equal to the square root times sine rg times sine theta, quantity sine theta minus mu cosine theta over cosine theta plus mu sine theta. Again, this is at 90 degrees. And so when we look at 90 degrees, the sine of 90 goes to 1, the cosine of 90 goes to 0. So this term is gone, this term is gone, this term just becomes 1, and this also becomes 1. So simplify this down. We get v is equal to the square root of g times 1. That's what the numerator becomes. And the denominator becomes mu times 1. And so we get v is equal to the square root of rg mu, the same exact thing. And so you'll see these in some horizontal circle problems. This concludes everything with centripetal motion. Again, if you have any questions, let me know. You should be able to do all the problems. Have a wonderful day, and we'll talk about Kepler's laws in our next assignment.